So I'm going to start by talking about a project that we were working on in my lab around 2016, 2017. So the idea, what motivated this project was like, when we observe this image, we can do some guesses about what this person is feeling in this image. We don't know about anything about this person. It's just one single image, but we can say, she's probably experiencing some pleasant emotion. She is showing affection towards the dog. She seems to be relaxed, laying on the floor in her apartment. So we can do all of these guesses about potential internal states or emotional expressions of this person. This is very challenging for a machine, but this is something that has been studied in computer vision for a long time, and most of the algorithms and systems that try to infer emotional states in videos or in images have usually been focusing on facial movements. And nowadays, we already have this type of commercial softwares that are very robust at detecting the face, detecting facial landmarks, and analyzing the configuration of these facial landmarks to recognize some prototypical facial movement patterns that usually are associated to prototypical expressions of emotions. The reason why there has been a lot of focus on facial expression analysis is because we communicate a lot with our faces. And to illustrate this idea, I'm going to show you, let's do an experiment, okay? I'm going to show you a video of a newscaster that is talking about news. In one video, is talking about a positive news. In the other video, is talking about a negative news. So you are not going to listen to anything, just you're going to see just the newscaster. And the goal is to guess which is the positive news and which one is the negative news. Okay, so video number one. No sound. Video number two. Okay, who thinks the positive news is video number one? Who thinks it's video number two? Okay, very easy, right? So we communicate. Oh, really? Okay, maybe there's something extra, but I think, really? Okay, but I think that the face is providing a lot of information, and you probably agree with me. Okay, so face provides a lot of information. Here is another example. So here you have another image. We run the same type of software. It says surprise. But what happens when we see the whole image? So suddenly we see that, this facial movement has nothing to do with emotion expression. This facial movement is about making an action. So we move our faces for several reasons, not just to communicate emotions. And more importantly, this is something that has been studied from in psychology, which is, it's very complicated to give an emotional meaning to an isolated face, because this is not how the world works. We don't see isolated faces, right? So this is one study where they were showing faces to participants, and they were asking to participants, so which one do you think is the emotion that this facial movement is expressing, or what is the emotion that this person is experiencing here? And people were not agreeing. But as soon as they gave you more context, there was more agreement, right? So what happens if you change the context? So it's the same facial expression, but a different context. And the contextual information is very subtle. So it's just a gesture, it's just an object. So they were running these experiments, and they were seeing how the context was strongly influencing the way you interpret these facial movements. And this is just one study, but there are multiple people that have been studying this context, this importance of contextual information. So at that moment, with my former student, Ronak and Jose and Adrià, two collaborators, we were studying this problem from a computer vision perspective. So the idea was, okay, we want to approach apparent emotional state recognition. So it's apparent emotion. I don't know anything about this person. I just have one image. But what is this apparent emotional state of this person? So not just by looking at the face, but looking at the context. And our hypothesis was that, if we can access the context, then probably we can do some finer grained recognition of things, like she is probably feeling confident in this situation. So at that moment, we were playing with different deep learning models. For this, we were trying to model this, right? So input is an image of a person with a context, and then output these apparent emotional states. And we didn't have data for that, so we were collecting data from public data sets like COCO, AD20K. Some of the data were actually manually downloaded from search engines by us. And then we designed these annotation interfaces. We had a lot of emotion categories because we wanted to be fine-grained with that. And what we were asking to the annotators was, okay, look at this image and think about category by category whether you think this person in this image is experiencing or this person in this image is expressing each one of these emotion categories. And then we're also collecting annotations on valence, arousal, and emotion, and dominance, which are the three most common continuous dimensions, and some demographics. So at the end, we had this data set with 23,000 annotated images and 34 annotated people. So one thing that we could do is observe a little bit. This is the co-occurrence of emotions. So how many images do we find, or how many people do we find in our data set that have been annotated with two emotions at the same time? And you find examples of affection and happiness, which makes sense. A lot of examples of anger and annoyance at the same time also makes sense. Almost no happiness and anger, so maybe just some noise, and no excitement and sadness at the same time. So it looked like everything was making sense. And then when we were experimenting with different types of modeling approaches at that moment, again, this was 2016, 17. So, but basically we were creating these two-stream neural networks. One of them was analyzing body features. The other one was analyzing the image features or the context features, and then combining these features and trying to estimate the discrete categories, the continuous dimensions, separately or in a multitask manner. So a lot of experiments. I'm not going to put a lot of time, so you can find a lot of results in the paper. That nowadays there are people that are doing more sophisticated things with this data set. But basically, the idea is that what we were observing is that in general we were obtaining better accuracies combining body and image. So if we consider the context, we were obtaining better accuracies. There was a significant difference on performance across categories. And one of the reasons is that there's a strong imbalance here. So how was this data set collected at the end? It was collected from images in internet, right? So people usually post images in internet if they are showing happy moments. So you have very low representation of anger, fear, pain, and so on, right? So this, of course, is affecting the modeling system, despite we were using weights and strategies to deal with this imbalance. But this is a problem, and this is something very, very common in emotion data sets. And then the performance was very low, so I'm not going to lie. So it's a very challenging problem. That's fine. We were above chance, but it was low. But what is important at this moment, so you can find more qualitative results in our papers and so on, but I want to mention the conclusions and lessons learned with this project that have been driving some of the research that has happening in my lab in the recent years. So, of course, the importance of seeing context in emotion perception and context in general. But there's another thing that is very interesting, which is we were studying a little bit the agreement level on affect-related annotations. And here, Justine yesterday was mentioning, right, that for some of these tasks, people perceive or don't agree. So people perceive different things. In this case, you see one image and you see the annotations of 5 different annotators. And what I'm showing here in the right is the histogram. So you have all the emotion categories, and then you have the voting. How many annotators say that they were seeing this specific emotion category? So what is interesting here is that if you show these histograms, and you have one annotator, then you have 2 annotators and show the histograms again, and you keep adding annotators, at a certain point, these histograms get somehow stable. So there's like a distribution that as soon as you have, what we observed is that as soon as you have like 20 annotators or more, this was somehow stable. So not everybody sees the same, not everybody agrees, but it's not random. There are some patterns. So we have some words where we have been studying this. I'm going to mention a little bit these studies later on. But first, I wanted to mention one idea, which is approaching emotion perception in the wild is so challenging. So it's challenging for us recognizing emotion of others. So doing this for a machine is very, very challenging. But one thing that you can do is restrict your domain. So try to study emotion perception in a domain that is very restricted. So one thing that we have been studying is emotion perception in the domain of assistive driving technologies. So the other day, Shiri was showing this autonomous car. That's very cool, but we are not there yet. So what is happening nowadays with the cars is that they are helping us to drive in a way that is safer and more pleasant, right? So The reason why the automotive industry is putting a lot of effort on that is because we experience extreme emotions while driving. So we spend a lot of time driving, and extreme emotions can affect our mental health and the road safety. So there's been a lot of research on trying to understand the experience of the driver, the emotional experience of the driver, and trying to create cars that can assist to have a better experience. And how does this work in general? So there are like 3 different pillars. First, sensors, right? You can be very creative here, putting sensors in your car. So very obvious, putting a camera, that's fine, or microphones, but then you can also put like pressure sensors in the steering wheel, and this is gonna give you information as well, or in the pedals, right? So you can be very creative here. Second, okay, you capture all these signals, right? But then you need to extract from these signals the information that is meaningful for the task that you are approaching. In this case, we were interested in emotion and particularly in stress. And then another component is interventions, right? So if suddenly the machine, the car, notices something that is going to affect your performance, what should the car do? So how you design interventions that are constructive and that really help you in challenging situations. So we were working mostly in the machine learning part. And here you have somehow a recent survey on assistive driving technologies and emotion recognition. And one thing that we observed is that most of the technologies focused on the car interior. So putting sensors in the car and trying to understand what was going on inside the car. But the reality is that you drive in a context, right? So it's not the same driving in a highway where there's no traffic and it's so convenient, or being in a city, right? So we were studying this. What is the emotion evoked by the road scene, and trying to understand this information as an extra signal that then you will need to combine with all of the other signals that you capture with the other sensors to make a better guess about the experience of the driver. Okay, so motivation. And here is a question for you. Which scene seems to be more stressful for a driver? So if you're a driver and you are driving, who thinks that scene A is more stressful than scene B? Who thinks the opposite? Okay, so scene A, there are a lot of things happening around. There's a lot of uncertainty. There are people, there are cars, whatever, right? And the other one is just straightforward. So our hypothesis is that some objects and events that are visible in the driving scene are informative to understand the current driver's subjective stress level. So how do we study this? So we were working with this data that we had where people were, so there are people driving, there's driver-provided stress, so it's self-report. We also have physiological signals, so electrothermal activity, heart rate, and respiration rate. We are not using this for now, but then we have a camera pointing out of the road and recording all of this video. And the idea is, okay, let's take all this video and let's try to create models that can infer the self-reported stress. And for that, we were using the effective road data set. This is a public data set. It has drives from 9 drivers, 55 minutes of drive, and then this continuous self-report, which we simplified the problem in 3 stress level categories. So these are the categories that we were working with: low stress, medium stress, and high stress. And then we were experimenting with a lot of models so this is like the single frame classifier, which basically in a timestamp t, you have this image, and then you try to infer the stress level at this timestamp, but then video models where you have a sequence and you try to output the stress time level at the end of this sequence. As you can imagine, the visual, so the temporal information is important, so we could get better results with the video models. And we were experimenting with different types of video models. We were experimenting with transformers, but with simpler convolutional neural networks as the one that I'm showing here, which is, it's relatively simple. So you have a convolutional neural network that is the same acting at each frame level, and then it makes predictions at each frame level, and then it learns a consensus to make the final prediction. So we were observing that this type of configuration was providing similar results, or statistically similar results, as transformers. We think that this model has already enough representation power for the problem that we are addressing. So the interest of using this simpler model is that we can apply here post hoc explainability techniques, and then we can learn more about the stressors of the road. So concretely, so this is in the first row, we have the original signal. This is a video that has been classified as high stress. And on the second row, you see what one post hoc explainability technique, it's called class activation map. So basically, class activation map allows you to show the regions of the image that contributed the most for the class that has been recognized in this video sequence, okay? So the way of reading this in this case is all of the red regions are the ones that contributed the most to recognize high stress level. So the interesting thing here is that you can also do semantic segmentation on the scene, and then you can cross the information of what are the objects that overlap with the red regions with a high level stress. And here you see a video of this, the segmentation original video, and then the objects that are overlapping with the high stress. But the nice thing here is that you can perform statistical analysis to see what are the objects that seem to be producing the stress, the ones that appear in the high stress level and that are contributing to recognize high stress, and that are not that present in the medium or low stress. And this is a bit related to what Justine was telling us yesterday about using explainability techniques to better understand what are the characteristics that are responsible or are contributing to recognize something that maybe we don't know how to explain in words sometimes. Okay, so this is the assistive driving technology for adults. I want to briefly mention one project that was inspired by this project, but this is an ongoing project. So we also have a project on assistive driving technologies for kids. And in this case, it's very different, the goal. So it's a huge team that is working on that. This is a very challenging project. But the idea is the following. So we have this car. So we made the conceptual design of the car following the same type of technologies that are used for adult driving. We equipped the car with sensors, and this was first design, and then it was sponsored by Hyundai, and Hyundai actually created the car with the sensors and so on, and it was shipped to Barcelona, and we were experimenting with this car. And the goal of this car is to be deployed in the hospital, and particularly to reduce the stress of kids that need to go through surgery. So kids that need to go through surgery experience a lot of stress. And what we do is, so the idea is to use the car to take the kids from the waiting room to the surgery room, and hopefully being able of distracting the kid, reducing the stress, and then capture vital signals right before entering to the surgery room. So this is what we are studying right now. So we have been deploying this car in the Barcelona Children's Hospital. The car is not, so it can be automatically, so that the interventions and everything can be automatically activated, but at this moment, everything is remotely controlled. We just run some pilot to see, what is the potential of this technology in this specific context. Okay, so some remarks so far. Importance of considering context to correctly understand emotion signals, emotion experiences. Second, I talked about scene context and situation context mainly, but there are many other contexts like cultural context or perceivers context. We have been studying a little bit the cultural context in large language models and so on. I can tell you more about this if someone is interested afterwards. But then the other thing that I mentioned is these individual differences. So I'm very interested in understanding these individual differences. And here, this is work that was done with my former PhD student Hassan and my collaborator Carlos Ventura, where the idea is studying the individual annotations. So first, let's see what is the common approach in emotion annotation. So usually imagine, for example, evoked emotion, right? Imagine that these samples are images and you are studying the emotion evoked by these images to an observer, right? So usually you have a collection of samples. So usually this is approach with supervised machine learning. So you need data and you need annotations. You have this collection of samples. And then you have different annotators. And each annotator is going to provide their labels for each one of these samples, right? And then at the end, you have a final annotation, which might be the average or the majority voting. And usually people think that this is the more reliable annotation. And the common practice is just to release and focus on the examples and on this average or majority voting annotation. But we think that there's a lot of information here in the different opinions that allow us to learn about the ambiguity and the individual differences across individuals in relation to affect and so on. And actually, again, this is something that Justine brought yesterday when she was explaining that, that for the report, elderly people in Japan and younger people in Japan, they had different opinions, and that's already interesting. So the idea here, so we have been experimenting with different data sets. I'm going to just explain the experiment with one data set. But here we were using the Cognimus data set. So this is a data set on emotion evoked by movies. So basically you have fragments of 7 Hollywood movies, and then you have 7 annotators. And our task is we have as input clips of 4 seconds, and we are trying to output the binary valence, so positive or negative, what each annotator is thinking. And so here is about, everything is about data. So it's a little bit what Alyosha was saying before. So we are not going to do anything fancy from a technical perspective, but we are going to compare 2 types of architecture. So one thing that you could do, which is the common practice, is just using one single task architecture. You have the input, and then you try to estimate this average opinion. Okay, the other thing that you can do is using a multitask architecture. So you have your input, and then you have different heads, output heads, and you're trying to estimate annotator 1, annotator 2, all your annotators plus the average at the same time, okay? So what is the hypothesis here? The hypothesis is that if you use the multitask architecture, you can learn a representation that is richer and that better explains all the features that are important for this evoked emotion. And then you learn this richer representation, and you are able to do a better inference in all of the annotators, including the average annotator. So here are the results for this specific experiment with this data set. And here you see all the annotators. This is the single task, and this is the accuracy binary problem, and this is the multitask. So you consistently see that you get higher accuracies if you use the multitask, and you also get higher accuracies in the average, right? Which is usually what people focus on. So this was consistently observed across the different data sets that we experimented with, that if we were modeling with multitask, we were getting better performances than in the single task. Another thing I didn't mention is that for some of the data sets, like the evoked emotions by videos, you have multiple modalities. You have visual, you have audio, and you can have the text transcripts, and you can also analyze the language, right? So when you combine all the modalities, you usually get better accuracies, and this is something that has been observed by other people as well. And finally, I think that our results motivate the interest of releasing, or at least studying, individual annotations in future dataset collection efforts. So now final considerations, and here is one philosophical slide. So one thing that I think is important to take into account when we think about emotion perception and this type of problems is the different ground truths or tasks that are present in the same scenario. And I think that sometimes this is not as clear as it should be. And here is one example. So a scenario of emotion perception. We have one target person, which is this person that we want to recognize the emotion, experience the emotion, perceive the emotion. So we want to recognize the emotion of this person. So what's happening here? So she might be experiencing some emotion, right? And this is about the internal state, which is what Shiri was mentioning yesterday, actually. That's very challenging. So this person is experiencing an emotion. Then there are spontaneous expressions. So these are movements that you do with your face or with your body that probably are a consequence of your internal state, and this is something that you cannot control. It's spontaneous, and this happens, and it's visible, so it's something that you can see. But then there's another thing, which is emotional signaling. So when you are interacting with people, sometimes you are making movements or gestures to intentionally communicate an emotion, right? And this is about social communication, but it's particularly about communicating engagement or other types of emotions that you want your listener to be aware that you are, communicating this. Perfect. And then you have the observer, and this observer perceives the emotion of this person. But again, this observer is influenced by the internal state. So there's a lot of ambiguity here, and that's fine. I mean, we just need to embrace that if we want to create machines that can deal with this correctly. That's what it is. I think it's exciting. I think it's challenging, but it's exciting. So often or sometimes, I think that one thing that is important is to properly discuss and understand the limitations of what we do here in the domain of emotions. So if we are working with these labels, we can never claim that our model that gets high accuracy is able of capturing experienced emotion. It's different. No, it's not going to do that. But all of these different ground truths or tasks are interesting and important. So one thing that I try to do is focusing on use cases. So we do in my lab some fundamental research about how to enable machines to understand emotions or to perceive emotions. But I also like to work on specific use cases. So some of the use cases that we work on are related to social robotics and human-machine interaction. And here we focus more on the spontaneous expressions and emotion signaling, and then medical or health purposes, and particularly in mental health. So we focus more on the experienced emotion. Here we are partnering with clinical psychologists, and we are interested in creating technologies that can do either early detection of mental health conditions or provide more objective information to better understand mental health conditions when someone has been already diagnosed. And my final slide, open questions, that's for Shiri. So open questions that I think are interesting. What is the role of emotions in learning? So I heard a lot these days about emotions implicitly somehow. Alyosha now was mentioning at the end that he thinks that pain and suffering, and sometimes he thinks this is very important for learning. But Alison actually has mentioned a lot of curiosity or engaging in play, which is having fun, right? Or the empowerment, which I think it's the emotional dimension of dominance. So I think that all of these modulate, there are studies that show how emotions modulate our attention. So I think that they play a very important role in learning, and I would like to learn more and understand more what is the role of emotions in learning. So then another thing that I think is very cool is how to use AI or machine learning to learn more about human emotions, even animal emotions. So animals also experience fear, and how can we, so during this workshop, we have seen a lot of excellent examples on how to use AI or machine learning to do larger scale studies to better understand intelligence or evolution or culture. So I think that doing this with emotions, and actually there are people already doing this with emotions, is very, very interesting. And finally, so the last question is, what simulated emotional skills could or should AI have? And here, I think it depends on the context, and I think it depends on the user as well. So maybe not all of us have the same preferences. So one thing is studying how to enable machines to deal with all of these emotional skills. And second is how do we want these technologies to be deployed in practice, and maybe we can have different opinions, and that's totally fine. Of course, we need to respect the user at the end. So that's my last slide. Thank you.
Great talk. Thanks. I was kind of wondering, you really focused on this like kind of stress example with the cars, and I was wondering whether that sort of like, so like how stressful is this situation or whatever? Do you know of any kind of like I don't know, studies like trying to correlate that with like the difficulty of self-driving? Because like, right, as humans, we get, this problem's too hard.
Yeah.
Run away.
No, I think that's an excellent question. I haven't seen any study as you are mentioning. Actually, no, I haven't seen any study, but I think that would be very, very interesting. I'm not sure if there's any data set that allows to study this directly, but I guess that you can take models, right, already trained, that make these guesses about the stress, and then cross this information with other data sets that might have information on difficulty. But I guess that I would expect a high correlation here.
This is a great talk, and I'm so glad you brought up the idea of diversity of annotation, because I think it's something that we tend to squelch. I know in my group we have four annotators, we throw out one, we calculate intra-class correlations, we jump through all kinds of hoops to come up with one value. And I'm wondering for emotion, why you think there's that diversity. Is it because the signal is polysemous? You know, it could have multiple meanings. Is it because there is no such thing as an emotion? Maybe this is a more philosophical question, but I'm interested in your thoughts
No,
about it.
I think it's an excellent question. I think it's a little bit of everything. So I think there's ambiguity of the data on the data. So often, if the stimuli is more complex, it can have polarity. You know, you can have a stimuli that elicits or evokes different emotions at the same time. So there's some ambiguity in the data. And then about the individual, there are so many things. It's in the internal state. Is going to affect the way you interpret a stimuli. Your personality, your preferences, your culture. So there are so many things here. And probably it's difficult to enumerate all of them, but so the more information that we have about the annotator and all of these factors that might impact the annotation in this case, I think the better we can be able of understanding all of this ambiguity. So another thing that we have been studying, and I think that there are other studies that do that, is when you when you annotate images, for instance, or whatever data, usually the annotators observe a sequence, right? So one thing that we notice is that the order they see the data influences the labels. So if you shuffle this order, you're going to get slightly different labels, and particularly in those samples that are more neutral, okay? Because the previous data that you have seen is affecting your internal state, and there's the contrast effect or the assimilation effect. So do I have an answer on what to do with that? No. So what's my advice? Collect the data, keep the data, you know? So if you are annotating something, keep the sequence, get as much information about the annotator as possible. So collect this information, because nowadays I think that we don't know how to deal with that. But the more knowledge we gain about the effects of all of these factors, if we have the data, the better we will be able of understanding this and you know, getting more knowledge on that.
Thank you.
I'll ask the last question. So my question is, you know, I feel there's a dichotomy between, you know, like, let's say last 10, 20 years of like research on, you know, like facial expressions of emotion and so on, which basically continuously says one thing, which is like that somehow people are just very bad at guessing like whatever emotion, you know, is in the picture, you know, that they're presented. And then maybe you add the body, it gets a bit better. Maybe add the background, it gets a bit better. But as you showed, right, it's still not perfect. And you just describe all this, you know, kind of confounding variables and so on. But at the same time, right, like I would argue that, you know, the evidence that, you know, we have these human civilizations everywhere. And, you know, like that this is based on the fact that actually we are actually quite good at, you know, understanding each other's internal states, and that we are actually like not that bad at it, you know, even with limited amount of information. So I guess my question is this, right? Like how much of the stuff that, you know, we think is studying, you know, like whether like expressions, you know, exhibit internal states and so on, is basically just studying you know, limits of language of how we describe emotion, limits of, you know, using these categories, you know, when you force people to on the spot give you one category, which kind of indicate it, right? When you ask different people, you get a bit more granularity. Suddenly you can, you know, do a better job, right? So clearly maybe the categories that you're giving are maybe not exactly how people would actually themselves, if they were not forced, you know, describe the, you know, the state of another person. So I guess my question at its core is, why are we not moving to more unsupervised methods, right? Why are we trying to predict these labels? Like, what do you think about that?
I agree with your question. And I think that moving to unsupervised and the work that she is doing is super cool. So I think that's really, really, and so yeah, I think that's very important. And maybe some more thoughts. Yeah, I think, so you made a lot of very interesting and relevant questions, and they just brought some thoughts to my mind. So one thing about the ambiguity, I think there's more consistency when you observe just one person, right? So in the evoked emotion, one person is going to be consistent. And when you said that we are good at inferring these internal states, we are much better at inferring internal states of those people that we know, because we are trained and we know about the individual characteristics. For other, inferring the states in more general situations, often you don't need to infer the internal state. It's just about communication, right? And you think that you are good at inferring the internal state, but maybe not. But maybe you are good at inferring the communicated state, and that's what is needed in this situation for a fluent communication. And then, depending on the use cases as well, sometimes getting an idea of the average annotation is okay. So I'm not saying that the average annotation is not useful. So, for example, if you think about evoked emotion by movies, right? And you think about filmmakers. They cannot care about each individual separately, right? So they need to care about the crowd, about if I do this shot in this movie is going to evoke in general, in the general public, what I'm intended to evoke, and that's fine. So this is also useful, right? But then if you are thinking about therapy and the importance of personalization for therapy, right? You are not okay with this estimation of the crowd opinion, so you need to focus on the individual. And there were other thoughts that came to mind, but maybe we can continue discussion afterwards. But there were very interesting points, yeah, what you said.
Great, thank you, Àgata.
Okay, thank you.
We're coming back.